Hello friends, myself Qazi Mansoor Ali. Next. Topic of discussion is Eigenvectors and Eigenvalues. An eigenvector of n by n matrix A is a non-zero vector x such that Ax is equal to lambda x for some scalar lambda. A is a matrix and lambda is the eigenvalue of A. There exists a non-trivial solution x, that is vector, we call that as eigenvector, for corresponding eigenvalue lambda. Example, let A is equal to the matrix 2 by 2, 1, 6, 5, U2, U 6 minus 5 and V 3 minus 2, where U and V are eigenvectors of A. Now we check AU, that is Ax is equal to lambda x is our condition. AU 1, 6, 5, U2, 6 minus 5. Now we multiply matrix multiplication. 1 into 6 is 6. 6 into minus 5 is minus 30. 6 minus 30 is minus 24. Next, 5 into 6 is 30. 2 into minus 5 is minus 10. 30 minus 10 is 20. So minus 24, 20, the column vector. Now we can take the maximum common element which can multiply to these two elements minus 24, 20 both respectively, that is 4. We have taken minus 4 as a common factor, so the column vector we get 6 minus 5. If you multiply minus 4 inside, you will get as it is minus 24, 20. So this minus 4 is nothing but the eigenvalue, and 6 and minus 5 is your u vector, that is eigenvector. AV 1, 6, 5, 2, V matrix 3 minus 2. Now we multiply 1 into 3 is 3, 6 into minus 2 is minus 12, 3 minus 12 is minus 9, 5 into 3 is 15, 2 into minus 2 is minus 4, 15 minus 4 is 11. Now only we can take one common from this, so 1 cannot be the eigenvalue we can consider here. We want a non-trivial solution, so we don't have any other element which can take two things commonly here. So V is not eigenvector for the matrix A. So only U is the eigenvector with corresponding eigenvalue minus 4. Next, characteristic equation. Lambda is eigenvalue of A if and only if the equation A minus lambda I of x is equal to 0 has a non-trivial solution. The set of all solutions of A minus lambda I is called as Eigen Space of A. The Eigen Space consists of the 0 vector and all the eigenvectors corresponds to lambda. The Eigen Space is the space which contains eigenvectors. Note, determinant of A minus lambda I, where I is identity matrix, is equal to 0 is called characteristic equation. Example, let A is equal to 4 minus 1 6, 2 1 6, 2 minus 1 8, that is 3 by 3 matrix, and eigenvalue of A is 2. Find a basis for the corresponding eigenspace. We have to calculate here basis. So first we consider A minus 2i because lambda is 2 given in the example. So 4 minus 1 6, 2 1 6, 2 minus 1 8 minus, now see here this is 3 by 3 matrix, so we consider unit matrix, that is I 1 0 0 0 1 0 0 0 1. If 2 multiplied inside, so the matrix become 2 0 0 0 2 0 0 0 2. We subtract the diagonal elements because subtraction is of diagonal elements only here. So 4 minus 2 is 2, minus 1 6 as it is, 2 as it is, 1 minus 2 is minus 1, 6 as it is. 2 minus 1 as it is 8 minus 2 is 6. Okay, so the three rows are same, so we can make by row operations the respectively two rows as 0 rows by operating the operations in R2, R2 minus R1, in R3, R3 minus R1. Okay, that is nothing but the augmented matrix to convert in echelon form. So only remains the R1, that is 2 minus 1 6 0 as a homogeneous system, 0 0 0 0 as a second row, 0 0 0 0 as a third row. Now the first place is for x1, second x2, third x3. Now we write that equation as 2x1 minus x2 plus 6x3 is equal to 0. We free here x2 and x3 as a free variable. So we write x1 as plus half x2 minus 3x3. Okay, so x1 is half x2 minus 3x3. Now we separate x2 and x3 there. So combination will become x2 1 by 2 1 0 plus x3 minus 3 0 1. We substitute for x1 as plus half x2 minus 3x3, x2 x3 as it is. So we get the vectors 1 by 2 1 0 as a first vector, minus 3 0 1 as a second vector. Now here 1 by 2 is fraction. We can remove that fraction by multiplying 2 to all the column elements. 2 into 1 by 2 is 1, 2 into 1 is 2, 0 into 2 is 0. So we can do here. So 1 2 0 as a free from a fraction vector. We never want a fraction term in the vector. So 1 2 0 minus 3 0 1 are eigenvectors of the matrix and which forms the eigenspace for the corresponding system. Next example. Find the eigenvalues of A. The matrix is 2 3 3 minus 6, that is of order 2 by 2. A minus lambda I, the basic condition. So 2 3 3 minus 6 minus lambda I. Now this is 2 by 2 matrix. We consider the unit matrix, that is 1 0 0 1. If we multiply lambda inside, lambda 0 0 lambda we get. So the subtraction is diagonal wise, 2 minus lambda 3 as it is, 3 as it is, minus 6 minus lambda. Now we take determinant, that is characteristic equation, determinant of A minus lambda I. So determinant of 2 minus lambda 3, 3 minus 6 minus lambda is equal to 0. Now we determinant is product of diagonal elements minus product of off diagonal elements. So 2 minus lambda multiplied to minus 6 minus lambda minus times 3 into 3, that is 9 is equal to 0. Now we multiply 2 into minus 6 is minus 12, minus 6 into minus lambda is plus 6 lambda, 2 into minus lambda is minus 2 lambda, minus lambda into minus lambda is plus lambda square, minus 9 is equal to 0. Next, so the simplification is lambda square, 6 minus 2 is 4 lambda, minus 12 minus 9 is minus 21 is equal to 0. Now we factorize 4 lambda in 7 lambda minus 3 lambda. We take lambda, the common part, so lambda plus 7 minus 3 in the bracket lambda plus 7, the common bracket lambda plus 7 into lambda minus 3 is equal to 0. So lambda plus 7 is equal to 0, lambda minus 3 is equal to 0. So lambda is equal to minus 7, lambda is equal to 3. These are the eigenvalues for the corresponding matrix A. Next, diagonalization. A square matrix A is said to be diagonalizable if A is similar to a diagonal matrix, that is A is equal to PD P inverse for some invertible matrix P and some diagonal matrix D. Students, a square matrix is a similar matrix if it has a diagonal matrix and the invertible matrix P in a such a way that A is equal to PDP inverse. This is the condition for similarity. Diagonalization theorem. An n by n matrix A is diagonalizable if and only if A has n linearly independent eigenvectors. If it has n linearly independent eigenvectors for corresponding matrix A, then we can say that A is diagonalizable. Example, let A is equal to 7, 2, minus 4, 1, the 2 by 2 matrix. Find a formula for A raised to K given that A is equal to PDP inverse. Now see here, P is nothing but 1, 1, minus 1, minus 2. D 5, 0, 0, 3. So P is the invertible matrix. So P inverse is nothing but 2, 1, minus 1, minus 1. That is, we can find the P inverse by operating the cofactor matrix. We have to calculate the cofactor elements here. That is nothing but the diagonal elements. So minus 2, we can write the diagonal elements and off diagonal elements we change and we multiply the determinant of the matrix P, that is minus 2 minus of minus 1, that is plus 1. Minus 2 plus 1 is minus 1. If you multiply minus 1, you get the inverse as 2, 1, minus 1, minus 1. Then by matrix multiplication, we can write A square as PDP inverse into PDP inverse. A square we can write A into A. What is A? PDP inverse. Again A, PDP inverse. Now we associate P inverse P. So students, we know that P inverse into P is identity, that is 1. So PD DP inverse we get. So D into D is D square. So A square we generalize as P D square P inverse. Now we substituted the value of P, that is matrix 1, 1, minus 1, minus 2 there, and D square. What is D? 5, 0, 0, 3. So diagonal square, D square we can make here diagonal square. 5 square is 5 square and 3 square is 3 square. And the P inverse is 2, 1, minus 1, minus 1 there. Next. In general, for k greater than or equal to 1, we can generalize A raised to k as P D raised to k P inverse. So P is 1, 1, minus 1, minus 2. And for square we have 5 square, 3 square. For k we have 5 raised to k, 3 raised to k. And P inverse as 2, 1, minus 1, minus 1. So you can consider the example number 2. Let A is equal to PDP inverse. Compute A raised to 4. What is P? 5, 7, 2, 3, and D is 2, 0, 0, 1. You have to compute A raised to 4. Next example. Diagonalize the following matrix if possible. The matrix A is 1, 3, 3, minus 3, minus 5, minus 3, 3, 3, 1. Find an invertible matrix P and diagonal matrix D such that A is equal to PDP inverse. Step 1. Find the eigenvalues of A. determinant of a minus lambda I is equal to 0 is a characteristic equation. So we subtract lambda from the diagonal elements. 1 minus lambda 3 3 minus 3 minus 5 minus lambda minus 3 3 3 1 minus lambda is equal to 0. Now we take the determinant. Determinant is nothing but plus minus plus, because first speaks the plus, second minus, third plus in the determinant. So product of diagonal elements minus of diagonal elements, that is the determinant. So 1 minus lambda minus 5 minus lambda into 1 minus lambda minus of minus 3 into 3 is plus 9 minus 3, second place is minus 3 minus 3 1 minus lambda minus of minus 3 into 3, that is plus 9 plus 3 minus 3 into 3 is minus 9 minus of 3 into minus 5 minus lambda is equal to 0. Now we simplify inside the terms 1 minus lambda minus 5 minus lambda 1 minus lambda multiplication, that is minus 5 plus 5 lambda minus lambda plus lambda square plus 9. In the second bracket minus 3 minus plus 3 lambda plus 9 plus 3 into minus 9 minus 3 into minus 5 plus 15 minus 3 into minus lambda plus 3 lambda is equal to 0. Simplify inside term 1 minus lambda lambda square plus 4 lambda plus 4 minus 3 lambda plus 6 plus 3 into 3 lambda plus 6 is equal to 0. So minus 3 plus lambda plus 6, 3 plus lambda 6 get cancelled because these are minus and plus term. Okay, it get cancelled. What remains? 1 minus lambda square plus 4 lambda plus 4 is equal to 0. So 1 minus lambda as it is, lambda square plus 4 lambda plus 4 we can write as a lambda plus 2 bracket square, because that is a quadratic equation. We can write in the perfect square form, lambda plus 2 square. So 1 minus lambda is equal to 0, we get lambda is equal to 1. Lambda plus 2 square is equal to 0, we get lambda plus 2 is equal to 0, lambda is equal to minus 2. That is 2 times, because lambda plus 2 square is there. So 1 minus 2 are eigenvalues of the matrix. Next, step 2. We have to find the corresponding eigenvectors for eigenvalues. The first eigenvalue is 1. So a minus lambda I. A is 1 3 3 minus 3 minus 5 minus 3 3 3 1 minus lambda is 1. So identity matrix remains 1 0 0 0 1 0 0 0 1. A minus lambda I is equal to 1 minus, the subtraction will take of the diagonal elements of A matrix only. 1 minus 1 0 3 3 minus 3 minus 5 minus 1 is minus 6 minus 3 3 3 1 minus 1 is 0. Now we reduce this matrix to echelon form. 0 3 3 minus 3 minus 6 minus 3 3 3 0. Now we interchange R3 to R1. 3 3 0 minus 3 minus 6 minus 3 as it is 0 3 3. We convert R3 to R1, R1 to R3. Now in R2 we perform the operation R2 plus R1. So we get R1 as it is 3 3 0. In R2 0 minus 3 minus 3, R3 as it is 0 3 3. Now again we perform in R3 plus R2. So we get R1 as it is 3 3 0, R2 as it is 0 minus 3 minus 3. The R3 changes to 0 0 0. In R1 we perform 1 by 3 R1. In R2 1 by 3 R2. So the converted matrix is 1 1 0 0 minus 1 minus 1 0 0 0. The third row as it is. Now first place is of x1, second is x2, third is x3. So we get the equations x1 plus x2 is equal to 0. From that we can write x1 as minus x2. In second, x1 is 0, minus x2 minus x3 is equal to 0. We consider the homogeneous system, that is regular. From this we get x2 is equal to minus x3. So we can substitute x2 in the first, x1 is equal to minus x2, we get x1 is x3. Okay. So we know the unknown matrix X as x1, x2, x3. So we substitute x1 as a minus x2 or x2 as a minus x1. We get 1 minus 1, 1. Taking common x1. x1 we have substituted as minus x2. x2 is as it is. Okay. x3 is x1. So 1 minus 1, 1 is the vector that we have get. x1 is as it is x1. x2 we can write minus x1 and x3 we can substitute here x1. So x1 minus x1, x1. So we take x1 common. So for corresponding lambda is equal to 1, we get the v1 vector we can call, or we can say as 1 minus 1, 1. Next, for lambda is equal to minus 2, a minus lambda I is equal to a plus 2i, because lambda is minus 2, minus minus will become plus 2 here. So a is 1, 3, 3, minus 3, minus 5, minus 3, 3, 3, 1, plus 2i. So identity, this is 3 by 3 matrix, 2 into 1 is 2, 0, 0, 0 into 2 into 1 is 2, 0, 0, 0, 2 into 1 is 2. Now we add, addition is there, we add diagonal elements to corresponding A matrix diagonal elements. 1 plus 2 is 3, 3, 3, minus 3 minus 5 plus 2 is minus 3, minus 3, 3, 3, 1 plus 2 is 3. We reduce this matrix to echelon form. So we perform the row operations there. In R2, we perform R2 plus R1. In R3, R3 minus R1. So R1 as it is 3, 3, 3. In R2, 0, 0, 0. In R3, 0, 0, 0. R2 and R3 becomes the 0 rows. In R1, 1 by 3 R1. We divide R1 by 1 by 3 R1. So the matrix is 1, 1, 1, 0, 0, 0. So R2 0 vector, 0 row, R3 0 row. Next. So first place is x1, second is x2, third is x3. x1 plus x2 plus x3 is equal to 0. We write x1 as minus x2 minus x3. x1, x2, x3, we can write x1 as minus x2 minus x3. Here we free x2 and x3 are free variables. We can consider there. So now we write the x2 row, that is x2. The elements is minus 1, 1, 0, because in third element there is no x2. For x3, minus 1, 0, 1. For second x2 there is no x3. So minus 1, 1, 0. This is, we can consider v2 vector, minus 1, 0, 1 as v3 vectors. So p vector, we consider the matrix of v1, v2, v3. Now we substitute v1 we have calculated for lambda is equal to 1, and v2, v3 for lambda is equal to minus 2. So p matrix is 1, minus 1, 1, the v1, minus 1, 1, 0, v2, minus 1, 0, 1, v3. And the diagonal matrix is, D matrix is a diagonal matrix, and which is of eigenvalues, and place the eigenvalues diagonally. The eigenvalues are 1, minus 2, minus 2. Okay, that is diagonal matrix, and off diagonal elements are zeros. So P matrix we have calculated, the eigenvalues we have calculated, the diagonal matrix also we have calculated. Next example, diagonalize the matrix if possible. The 3 by 3 matrix is given: A 2 4 3, minus 4 minus 6 minus 3, 3 3 1. The characteristic equation of A is determinant of A minus lambda I is equal to 0. 2 minus lambda, directly we can subtract the lambda from the diagonal elements. 2 minus lambda, 4 3, minus 4 minus 6 minus lambda minus 3, 3 3 1 minus lambda is equal to 0. This is characteristic equation. Now we multiply the diagonal elements and subtract two off diagonal elements, that is determinant. So first plus, second minus, third plus. This is the determinant concept. 2 minus lambda, minus 6 minus lambda, 1 minus lambda, minus of minus 3 is plus 9. 3 into 3 is 9. Minus 4, minus 4 into 1 minus lambda, minus of minus 3 into 3 is plus 9. Plus 3 into minus 4 into 3 minus 12, minus 3 into minus 6 minus lambda is equal to 0. See here, 2 minus lambda we multiply here to the element minus 6 plus 6 lambda minus lambda plus lambda square plus 9 minus 4 plus 4 lambda plus 9 plus 3 inside the bracket minus 12 minus of minus plus 18 plus 3 lambda. We multiply inside the terms, so we get this equation. Now 2 minus lambda, simplify it, lambda square plus 5 lambda plus 3 is the simplification, minus 4 plus 4 lambda plus 5 the simplification, and 3 lambda plus 6 is the simplification. So further simplification, if you make, we get the equation as minus lambda cube plus 3 lambda square plus 4 is equal to 0 as a simplification. You can check it. Now if we simplify, the eigenvalues are, you can find out on calc also, the eigenvalues are lambda is equal to 1. So lambda minus 1 is the factor, and lambda plus 2 bracket square is equal to 0. This minus you can divide here. So we get lambda is equal to 1, minus 2 as a eigenvalues. So for lambda is equal to 1, we get the corresponding eigenvector as 1 minus 1 1, as like we have calculated in this. So 1 minus 1 1 for lambda is equal to 1, and for lambda is equal to minus 2 we get minus 1 1 0 as eigenvectors. Okay, so it is impossible to construct a basis because we have the two same eigenvalues here. So we cannot diagonalize the matrix because of the eigenvalues are same. Okay, so whenever they ask you to find out the diagonalize the matrix, first you have to calculate the eigenvalues, and from that eigenvalues you have to calculate the eigenvectors, and the procedure is explained in last example, that is previous example. Next, determine if the following matrix is a diagonalizable. A is 5 minus 8 1, 0 0 7, 0 0 minus 2. Now see here, the matrix is the triangular matrix. In triangular matrix, the diagonal elements are the itself eigenvalues of that matrix. So there is nothing required to calculate here by characteristic equation. Once again I am speaking, in triangular matrix, that is upper triangular matrix, the diagonal elements itself are nothing but the eigenvalues of that matrix. So phi u 0 minus 2 are the diagonal elements, and that itself plays the role of eigenvalues, and these eigenvalues are distinct. So we can say that this matrix is a diagonalizable. If anyone asks you to check this is the diagonalizable or not, you can utilize this concept here. Next, theorem. An n by n matrix with n distinct eigenvalues, then it is diagonalizable. Already I have explained, if the eigenvalues are different, we can diagonalize. Okay, as a diagonalizable concept. Diagonalize the following matrix if A is equal to phi u 0 0 0 0 phi u 0 0 1 4 minus 3 0 minus 1 minus 2 0 minus 3. See here, this is a lower triangular matrix. Now see here, the zeros are in upper side, so this is lower triangular matrix. The non-zero terms are in lower form. So this is lower triangular matrix. Again, the diagonal elements are nothing but the eigenvalues. The eigenvalues are phi u minus 3 minus 3. So we can find the eigenvalues are repeated, phi u minus 3 minus 3. But once phi u minus 3 are distinct value, we can diagonalize it. For lambda is equal to phi u, we get the eigenvector as minus 8410 and v2 as minus 16401 as a two vectors. Okay, and for basis, for lambda is equal to minus 3, we get v3 v4 vectors, that is 0 0 1 0 and v4 as 0 0 0 1. So the P matrix we can write v1 v2 v3 v4 column wise, that is P is equal to minus 8410 minus 16401 0 0 1 0 0 0 0 1. This is P matrix. And diagonal matrix, that is eigenvalues are nothing but the diagonal elements. This is lower triangular matrix. So phi u minus 3 minus 3. So off diagonal elements are zeros. Now in this v1 v2 v3 v4, you can solve it for lambda is equal to phi u, lambda is equal to minus 3. You try it. So thank you for this video.